right, wonderful. Thank you.
Hello, everybody. I'm Guglielmo Faggioli, and in this joint work with Nicola Ferro, Raffaele Perego, and Nicola Tonellotto, we asked ourselves whether we actually need all the dimensions in when we use a dense representation in information retrieval. Okay, to give you a very quick recap on dense information retrieval, we know how it works. We take our queries and documents, and then we project them in a latent space where hopefully relevant documents will be somehow in the proximity of the query. The problem is we do not really have control on what happens on those dimensions, which are latent, and possibly they might encode some kind of noise. So maybe not all of them are useful. And our hypothesis is motivated by two other well-known hypotheses. The clustering hypothesis, which states that documents associated together tend to be relevant to the same query, which we all know because it's a very well-known hypothesis in information retrieval, and also the manifold hypothesis, which is typically used in deep learning and is based on the idea that real-world data represented in high-dimensional spaces tend to concentrate in the vicinity of manifolds which are of much lower dimension. So we tried to combine these two different words, the IR and the deep learning words, with a new hypothesis, which we call the manifold clustering hypothesis. In this case, our idea is that high-dimensional representations of queries and documents relevant to them often lie in a query-dependent, lower-dimensional manifold of the representation space, which, to give you a more grounded description, simply states that instead of using all the dimensions in a dense representation space, we might be able to get better results, better retrieval results, by focusing on manifolds, so smaller dimensional representation space. To validate our hypothesis, we pretty much have two main research questions. First of all, we need to understand whether there is some kind of evidence that supports our hypothesis, which practically speaking means to look for some kind of lower dimensional space where our retrieval is more effective, or in other terms, where documents tend to be closer to the query. And the second challenge is to determine how we can find such manifolds. So one problem with manifolds is that they are actually infinite. There are a lot of them, and we obviously cannot verify, we cannot look at every single manifold in the space. So instead of looking for a generic manifold, we focused on a very specific category of manifolds, which are actually the linear subspaces. So in simple terms, imagine you have your representation in 768 dimensions, and then you simply drop some of the dimensions, okay? This must be done both for the queries and for the documents, and at that point, you are able to compute your inner product in that linear subspace. Even though we focused on linear subspaces, which are way less than the infinite manifolds, still there are a lot of linear subspaces as well. In particular, if you consider, again, 768 dimensions, you have at least 2 to the 768 possible linear subspaces. Way too much to be explored to explore all of them. So the solution that we adopted was to introduce an additional assumption, which consists in assuming that the dimensions are independent. So what we hypothesized is that each dimension provides some form of, can be associated with some form of importance, so we can say which dimensions are more important than the other in a completely independent way. So we don't need to look at other dimensions to decide which are the most important. Obviously, both of them, the linear subspaces and the independence, are simplifications done for simplify our problem, but they also, we can hypothesize that going with classical manifolds and ignoring this assumption, we can find even better results than what we found. So to find the best dimensions, we designed a novel class of systems, which we called dimension importance estimators. The idea behind a dimension importance estimator is to give some form of estimation of the importance of each dimension. So what you need to instantiate a DIME, the acronym for Dimension Importance Estimations, is the query, the dimension, the index of the dimension for which you want to estimate the importance, and the representational model. And additionally, possibly some other parameters and external information. Once you combine these elements within a DIME, you get in output a real value which describes how important each dimension is. It's very similar to feature selection and feature importance estimation, after all. You have your representation and you need to identify which are the most important features. The difference with feature selection is that in our case, we don't really have a semantic meaning associated with each feature, but the dimensions are latent and do not have actually a semantic meaning. So once we have our DIME, which at the moment we consider it a black box, we assume to have our query representation, so the vector describing the query in our latent space, and we compute for each of the dimensions its importance. Then, using this value, we are able to rank dimensions according to their importance. What we do at this point is then to preserve only the most important dimensions. The idea to simplify everything is to zero out all the dimensions that have low importance. In this way, we don't need to change the index. It can remain exactly the same, and we can operate only on the query by zeroing out some of the dimensions, and in this way, we make sure that those dimensions do not contribute to the inner product, and thus we obtain some sort of projection within a linear subspace. So, to validate our hypothesis, we tried with some practical experiments. In particular, we considered three pretty much state-of-the-art dense information retrieval systems, ANSI, TASB, and Retrieval, and for collection. Three of them are based on MS-MACO, Deep Learning 19, Deep Learning 20, and Deep Learning AD. And in this case, we can evaluate our dimension importance estimators in, let's say, in-domain setting. And we also considered the robust collection, which is based on the TIPS corpus, so it can be considered an out-of-domain collection. To answer the first results question, we designed an oracle, so a system based on the actual relevance judgments and labels. And we used it to verify how well we are able to recognize which dimensions are the most important. We have our query representation. We have the representations for all the labeled documents, so the documents actually from the QRLs. And we use the ADAMAD product between these two representations to construct an interaction matrix. Then, obviously, if you look at each column of this interaction matrix, the columns that are more correlated with the relevance judgments are those that are most likely to give you a better ranking and so can be considered more important. So we computed the correlations between the columns of the interaction matrix and the relevance judgments and obtained an importance estimation for each of the dimensions. Here you can observe the performance that we can achieve using our oracle. So the dashed line is the baseline when you use all the dimensions, and the curves describe how the performance changes when you keep only part of those dimensions. As you can see, for example, when it comes to the Deep Learning 19 and DCG, we can get up to plus 18% improvement. While if we consider the robust collection, the improvement is as big as plus 62%. So this, first of all, validates our manifold clustering hypothesis. Indeed, dimensions are not all the same, and some of them encode some noise. And this is particularly evident in the out-of-domain setting. In fact, since the representation was not trained there, it's more likely that dimensions contain more noise and are less useful. When we remove them, we have a pretty huge improvement in terms of performance. The only strange case is represented by ANSI, which constantly increases its performance with more and more dimensions included, until we reach the last 20 to 10% dimensions. Those dimensions are so bad and so noisy that they cause huge drops in terms of performance. So if we were able to just recognize 20 or 10% of the worst dimensions of our representation, we would be able to get an improvement of plus 62%. Then, once we have proved, let's say, our hypothesis, we can try determining some more practical DIMEs. So, the first DIME that we tested is based on LLMs. We just take the query as prompt, we feed it to the LLM, and we generate a pseudo-relevant document this way. And we compute the Hadamard product between the single document generated through the LLM and the representation of the query. And we obtain again the vector describing the importance of each dimension. Again, we use this vector to filter out the dimensions that are the least important, and these are the performance that we are able to achieve. As you can see, especially for Contriver and TASB, the improvements are pretty big, up to plus 11.4%. And moreover, they are significant even with just 40% of the dimensions. Throwing away all the dimensions beside the first 40% still allows you a huge improvement. And ANSI, on the other end, as we have seen before with the Oracle, tend to have a slightly clear behavior with a nice improvement, although not significant. The second DIME that we tested is based on actual active feedback. So in this case, we assume to have a relevant document. It's enough to have just one single relevant document, which is not that much to ask for. For example, we can consider the document clicked by the user on a SERP, and there are plenty of scenarios in which we have one relevant document, such as legal IR, e-discovery, and systematic reviews. And again, in this case, we have a pretty huge improvement, which can be up to plus 34.4%, for example, on task B, using again the robust collection, so where we observed more noise. So, indeed, what we observed is that if we were able to recognize which dimensions are the most important in a dense representation, we could greatly improve the performance of our system. And the advantages of this approach is that the only thing that it requires you is to zero out some of the dimensions. You don't need to reindex, you don't need to retrain anything. Simply by looking at the representation of the query and removing some of the dimensions, you can get up to plus 34% in a realistic case, or up to 64% improvement, 62% improvement in the oracular scenario. As future development, we are interested in automatically determining the number of dimensions. In this case, we looked at fixed cutoff, and also trying with nonlinear times and actual manifolds. That's it. Thank you very much.